Nick here, M0NTV, and welcome back to my shack and to another homebrew video. Now, today we're going to build the microphone amplifier for this transceiver. And we're going to use a tremendous little chip called an SSM2167, which you can buy on a little breakout board. And the good thing about this is it not only will amplify our very weak signal from the microphone, but also it's got a built-in compressor. So we can actually have some audio compression, which will make our audio signal a bit more punchy when it gets modulated onto our RF signal. So it's a really great little thing. Now, if you're getting shades of deja vu about this, thinking, well, I already seen a video about this. Yes, you have. I have already made a video building this same design, but crucially, about a year ago, I found out some stuff about this chip and this board in particular. So this second video has been a long time coming, really, but means that I've really got to kind of redo this because I've learnt some things that actually will make a big difference in the way that you handle this chip, and particularly if you buy these boards and use them. So, if you're intrigued, good. Keep watching, and hope you enjoy. Well, here is the SSM2167 breakout board, and you can see clearly here the chip itself, and then there's just various capacitors and resistors hanging off these pins. Now, about a year ago, I was contacted by another home brewing ham, Dave Stoney, G8PTN, and he'd done some work on this and discovered something that I'm not sure anybody else has discovered. If they have, they haven't reported it. And I'll try and show you what Dave found out, and I'll show you some of his findings in a moment. But essentially, the main work here is done by these two resistors. So you've got R1 here, which, as you can see, is connected to pin 7 on the chip. And then R2 is connected to the next one up, to pin 8. Now, pin 7 controls the gate threshold, and pin 8 controls the compression ratio. And you can see there's potential there to put some other resistance in if you want to take these out, or put potentiometers in there, or whatever you want to do to mess around with that. But as it is, Dave actually did some research on this and some measurements, and realised that as it is, this thing is doing no compressing at all. All it's doing is limiting. And I've actually built a couple of transceivers using this as it is, thinking I'm getting compression, but never actually testing it, assuming that that it's going to do what it says, but the truth is it doesn't, because I don't know how this has happened, but every board that I've had of these, I've had a few of these now, so I've tested them, and they're all the same. These resistors are in the wrong place. R1 is where R2 should be, and R2 is where R1 should be. So the values are right, but they've just been soldered in the wrong place. So actually what you're getting is just a limiter, but no compression at all. And what Dave did is he actually desoldered these, swapped them over, and found that it actually did what it was supposed to do. So well spotted, I mean, it just goes to prove, don't believe everything that you see. So what I'm going to do is I'm going to do that. I'm going to desolder R1 and R2, and I'm either just going to swap them over,
Or if that's a bit too fiddly, what I'll do is I'll use these holes here. So these two are connected together, and this, so I could just stretch a through hole resistor over there and there and there and there, and see if I can actually get this to do what it's supposed to do and actually do some audio compression and not just limiting.
So, just in case you're in any doubt about this, this is just a blow-up, really, of a still of that video I've just shown. And you can clearly hear, I've got my big cursor here, you can clearly see now R1 and R2, and how R1 is connected here into pin 7, and how R2 is connected into pin 8. And now these resistors are soldered in the wrong way around. They're also soldered in upside down. That doesn't matter, but these numbers you're reading back to front and upside down, but that is actually 1, 0, 2, so 1, 0 and 2, 0, so that's the 1K resistor, and this is 1, 5, 3, so that's 1, 5 and 3 zeros, so this is the 15K resistor. So actually, you know, if I thought about it, which I didn't before, and I'd got a magnifying glass, I could have looked and seen that these were in the wrong place. And incidentally, you know they're in the wrong place because if you look at the data sheet of the chip itself, it actually tells you and it gives you some alternative values for these two resistors so that you can adjust the gate and the compression ratio. So I could have seen, but what I did in fact was I just put the multimeter on here and here and here and here and measured the resistance and saw it was just as Dave discovered. These two are in the wrong place. So that's what I'm going to do. I'm going to take them off and I'm going to put my own through hole resistors in here and here. Now just before I show you what I did, let me just give you a quick look at Dave's experiments and the results that he kindly sent to me. So now he pasted some stuff from the data sheet. This is the chip itself, and you'll see clearly here pin 7 is the gate threshold, pin 8 is the compression ratio. And as I said, you can play around with those two resistors and get different values. Now what it's supposed to do and would do if the resistors were soldered in the right places is that it would come with 2-to-1 compression ratio with that 15K resistor, and with the 1K gate resistor would give you a minus 48 dBV noise gate. Now, this is what Dave found. With the resistors as initially fitted, you get this. So you get the amplification, and what he did, of course, is he plotted the voltage in against the voltage out, and so you see this amplifying, and then whoa, it just stops because it's limiting and it gets to that. So there's no compression there at all. It just amplifies and then it stops. And as I said, you know, I've put some of these in my transceivers before thinking that they're going to be compressing, and they're not actually compressing at all, they're just limiting. So what Dave did is he swapped those over, and when I say swap them over, he didn't just swap them over. What he did is, well, he kept the 1K for the noise gate at the minus 48 dBV, but he played around and actually put a 56K resistor in the compression slot, which actually gives you a different amount. It actually gives you a 4.2-to-1 compression ratio. So that, just bear that in mind when you see my results, because I literally swapped them over. So mine will only be a 2-to-1 compression ratio. But so that's what he had before, and this is what he found. Wow, look at this. Look at the blue line in particular. So now, look how the slope of that blue line now. So this is doing what a compressor is supposed to do. You know, it kind of makes things louder at quieter volumes. So, you know, when you're speaking more quietly into the microphone, you don't need much more voltage here on the input to see much greater voltage on the output. That's what you want until you get to the knee, this point here. which is this gate threshold, and you'll see it was supposed to be minus 48 dBV, and it just about perfectly is. If we drew a line down here, that would be about minus 48. So you can see then, and it just ramps up at a much more gradual rate then until you finally get to the top limit. So it's going to kind of smooth out those higher voltage things will be limited far more than the rest of it. So, you know, it's doing what it's supposed to do. Well done, Dave. And I thought when I saw this, well, you know, I need to try this out for myself.
So here is my board, and you'll see very easily I removed those two surface mount resistors, R1 and R2, and I used the conveniently placed little through holes there to put two through hole resistors. And so I've got it, and I've done it, and that's fine. So the next thing then is to test it for myself.
So how am I going to test it then? Well, I need an audio input because I want to test it. Eventually it's going to be connected to a microphone, so so I need an audio input, and then I need some way of measuring the output so I can see what happens with the gain. Well, the audio input is fine because I've got a signal generator, and that'll, you know, go right up into RF frequencies and right down into low frequencies, so I can do that. But how am I going to measure it was an interesting question. So I thought, well, I can't use a spectrum analyzer because that only goes down to 9 kilohertz. And all right, yeah, I could use a higher audio frequency, but I'm thinking, you know, I really want to test this at the frequencies I'm going to use it. I've got a 2.4 kilohertz crystal filter, so the whole audio spectrum is going to be contained within that. So really I want to put a 1 kilohertz sine wave into this thing and see what it does with it. So I couldn't use the spectrum analyzer. Well, I thought, well, I'll use the oscilloscope. But the problem is with my oscilloscope, and I say it's with my oscilloscope, I mean, it may be a combination of all my equipment, but it's not great with very low voltage levels. So when you get down really low voltage levels, it gets a bit noisy, and the trace jumps around a bit, and it's not great really. And I'm just thinking, well, it's probably not going to be all that accurate. So I was thinking, well, what am I going to use? Then I had an idea.
I realised I could use my digital multimeter because my multimeter, which is an excellent one actually, as you can see then, it's a Bryman BM235. It's a true RMS one, so I mean, it's no good trying to put RF into it, but for low frequencies and audio frequencies, yeah, you get a good RMS reading on this thing. Incidentally, this is a tremendous meter. I got it. You'll see it's badged with the EEV blog, and if you follow Dave Jones's channel, you'll know he likes to rip things apart and put them through their paces. And I bought it because this thing, he compared it against much more expensive flukes. And this thing wiped the floor with them all. It was, in terms of its accuracy and everything, really good. And I mean, it's not cheap, but it's a lot less expensive than some of those high-end flukes. Anyway, other multimeters are available, but the only reason I tell you that is that it's one I trust. So I've got a few multimeters, but this is one that I trust the readings of. And yeah, so that will measure RMS, millivolts. And so that's what I did. So I set it up, I put 5 volts, make sure it's 5 volts, please don't put 12 volts, into the SSM2167 board. And I connected the signal generator up to the input, and I connected this bad boy up to the output, and I made some measurements. And I'll show you now those measurements that I made. And so here are my results. I've got a big sheet of paper, And so I recorded the input on the signal generator, and I started at 1 millivolt, peak to peak. And then I recorded next to that the output that I measured on my digital multimeter, but this is RMS in millivolts. So, and I just incremented by 1. Started for 1 and went up all the way here, all the way down, all the way down here, all the way down here. Yes, it goes over the page. Look at this. All the way down to 60. When I got to 60, I got fed up. So I decided I was going to increment by 10 then. So 70, 80, 90, 100. And I carried on incrementing by 10 all the way down to 500. And I got fed up again and thought, okay, I'll increment by 100 millivolts. And I did for these last few, right up to 1000 millivolts, 1 volt. So there's a lot of figures there. And obviously the input, I'm recording that measurement peak to peak voltage, but the output is RMS. So it's clear I'm going to have to do some calculations, and I want to produce a chart. So what I needed to do was to throw all this into a spreadsheet, and that's what I did next.
So the first thing I did was to transcribe all those figures that I recorded on that big bit of paper down into a table. So that's this row here, this column here, and this column here. But I wanted, first of all, to make sure that I was, dealing in the same. I've got peak-to-peak voltage here. I'd got RMS voltage here. So I thought, well, let's change the peak-to-peak to RMS. So then I can have the input and output the same. So I did that. So that meant that I needed to use a simple formula. So down here you'll just about see, basically that's just takes the peak-to-peak voltage, splits it in half to get the peak voltage, and then multiplies that by 0.7071, which gives you the RMS voltage. So that I did that. So now I've got RMS input, RMS output, but that wasn't enough because I actually wanted to be able to compare my graph as like for like as much as I could with the one that Dave did. So that meant I needed to convert it into dBV. So this is decibels reference to 1 volt. So to do that, basically what you need to do, it's 20 times the log of the RMS over 1000, because I'm in millivolts. So it's 20 log the RMS divided by 1000, and that will give you the value in dBV. So I did that for the input and the output, and got these figures then. So then what I did was I threw those figures, these figures here, into a chart, and this is what I got. And actually it's remarkably similar to the one that Dave produced from his values. And I think, well, the only thing to really point out, I mean, it works in a similar way. You'll see how sharp this line here is, which equates to the fact that this is input voltage, but we could think of this really as kind of input volume, really, in terms of how loud you're going to be speaking into a microphone. And you'll see, you don't need to speak very loudly to get quite a lot of gain out the other end, which is exactly what you want, because the reason I'm using it is to make the signal more punchy, so I can get a bit more volume out of the microphone amp, and a bit more of a kind of punchy signal then going through the IF section. The knee, where this curves round and we start to get this real compression happening here. Look at this, minus 48.20. That marker is there. So again, we're in the right figure there for that minus 48 gate threshold. And once again, instead of just tracking up here and flatlining like it would have done, and I regret I haven't got an old unaltered one now, actually, because I would have done that test on the one before I'd swapped the resistors over. But I've swapped the resistors over in all the ones that I've now got lying around. But that's I imagine it would look just the same as Dave's looked before. It would go up like that and flatline, whereas this does this properly and then compresses before you actually limit it at the top here. So I'm pleased that my results accord very well with the ones that Dave produced, and so I'm satisfied that the SSM2167 board that I have is now in fact compressing in the way that I want it to. So then the next challenge now is to put some other components with it and turn it into a microphone amplifier that I can use in my radio. Now, those of you that have watched my previous video on building this design will perhaps be familiar with this schematic, except to say this is just really a smartened up version of that pencil scribbled one that I showed in the previous video on this, with the one exception that I got the gate threshold and the compression ratio pointing to the right resistors this time, because last time I had the compression going to R1 and the gate going to R2. So I've corrected that, but other than that, it's just a smartened up version of what I built last time. And so having now got the right resistance values in R1 and R2, I thought we're probably good to go. So I thought I'll have a go at building it. And before committing to solder, I thought I will breadboard it first and see what it looks and sounds like. And that's what I'm going to show you now. So I breadboarded up the circuit, and because I didn't solder any of the leads on, I got all these little clips just hanging on to the ports there, so it's a bit messy, but anyway, it's functional. But very quickly I realised I had a problem. And now notice I haven't even actually got the microphone plugged in yet, but even with no audio input, I'm just going out to, it looks like a cassette tape. It's actually a little speaker, high impedance speaker with a little audio preamp built in, so it's battery operated, so it's great for testing. But with it powered on, 5 volts going in, and I'm just going to here, this is what you get. So it's like a metronome, and let me show you what that looks like on the oscilloscope. And so all I've done is just replace the speaker with my oscilloscope probes, and let me show you what it actually looks like on the screen. Now, get a load of that. So you can see we've got a very regular pulse, 2.7 hertz. Look at that, I mean, it is almost a perfect metronome. And I thought, well, what on earth is causing this? And I tried a few things. Now I tested the SSM 2167 board on its own, and I wasn't getting this. So I knew that the problem had to be with some of the additional circuitry that I've built around it to use it with a microphone. And I tried a few things, more capacitors to ground and various things, and nothing worked at all until I tried this. Now, just a minute, get a load of this. Gone.
absolutely gone. And all I did was to short out that 470 ohms resistor that is in the VCC line, so which is this one here, and very, very interesting, because if I put it back in circuit again and we look down, we're back to the pulse. And you take it out, short it out, pulse gone. And I think what was happening was that actually that the purpose of that 470 ohm resistor was a current limiting device. But I think that the trouble is, looking at the amount of current that the thing needs. So if we kind of go down here, this is not desperately accurate, but you'll see what we're drawing, and actually we're drawing 2 milliamps then, but it will occasionally peak to like that to 3. So clearly we need kind of high 2 milliamps to 3 milliamps to run it. The problem is with that 470 ohm resistor in series, you're dropping a volt over that resistor, and we're only feeding it the whole thing 5 volts, so it's limiting the current too much, because that by putting that in and dropping a volt over it, you're getting something like 2.12 milliamps maximum is being fed into the rest of the circuit, which is just not enough. So I think that is what was causing the problem. I was just not feeding it sufficient current, and so once I did realise that and took that out of circuit, then it works absolutely fine.
So having got it working successfully and having ironed out all the little problems and the rest of it, I decided it was back to the schematic now to adapt it to precisely what I wanted it to do. So here is the final version of the schematic. You'll see I've removed the offending 470 ohm resistor in the 5 volt line, and I've just made a few changes to incorporate this switch here, because obviously this switch is important in my radio, because I want to be able to switch the line coming in to the board between the input from the microphone and the input from the Arduino, the tuning tone, which is accomplished by this switch, and I've reflected that there in the diagram. The only other thing to mention is the 10K trimmer that you'll see there, and that just controls how powerful your output from the amplifier is. So it's effectively a gain control, and you can tweak that up and down depending on how much you want to feed into the balanced modulator, and that will be kind of trial and error really, and we'll perhaps see that a little bit more on the next video when we do some transmission tests. So I've got the final schematic, and this is what I built.
So we're back to the front panel, and I thought what I'd do is I'd actually build it and fit it in and get it working with the rest of the stuff. So you can see, if you watch that video I did in the front panel, I've added a few bits, you'll see those in a minute, but most importantly is bottom right down there the microphone jack. So I'm going to just flip this around now and show you what it looks like on the other side. So here it is. Now you see I've fitted the loudspeaker since the last video, even though I haven't got the audio amplifier yet, but that's on there. And rewired one of the switches, which is pertaining to what I'm about to show you here, which is the microphone amplifier. Here it is. I glued it. Let's just get this to focus. Glued this on the end here. There we are. And so it didn't take up too much space on a little bit of strip board. And you can see down the bottom there, that's the other side of the microphone jack with those different leads going off. And you've got the yellow and the purple lead, which are going off there to the other side of this double pole, double throw switch, which is the tuning tone switch. So half of it goes to the Arduino to engage the tuning tone, and the other half is controlling what goes into the in socket or the in pin of the SSM2167, and depending on where you flick the switch up or down will determine whether you're going to get input from the microphone or input from the Arduino, i.e. the 1 kilohertz tuning tone. And yeah, so that's what it looks like. So it doesn't take up much room, which is brilliant. So I can that's one less board I've got to stack anywhere else. And let's have a look what it looks like in action. So I've got the thing fired up now, and that's just an external PTT, and I've got a little microphone going to go into that in a minute. But what I want to show you is the screen of the scope. I'm going to try and balance this whilst doing everything else. Should be fun, and show you what I mean. So what I'm going to do is I'm going to flip the PTT on now. One, two, 1, 2, 1, 2, testing, M0 NTV, Mike 0, November, Tango Victor, testing, 1, 2, 1, 2. And as you can clearly see, we are compressing because you've got all those spikes that are only extending up to a certain level. And if I speak a bit louder, you'll see that that's exactly happening. I'm compressing that waveform. But if I speak a bit quieter, you'll hear that I'm not compressing. So we've still got some dynamic range. So if I'm speaking in my normal kind of voice, we're getting up there to that compression level, which is exactly what you want, really. You want some dynamic range because we've all heard over compressed audio, and it's not very pleasant to listen to. But so I think this is pretty good, really. So I mean, it's doing now what I want it to do, and hopefully it will give my signal a bit more punch. But I'll just show you as well when I flick the switch now, and what that switch will do. Well, let me just turn the PTT off first, so we're back in kind of receive mode. And this is still on because I've not turned the microphone off. Actually, I've just turned the PTT off. But in reality, when the transceiver is built, you won't have anything coming through the mic because there won't be any bias going into this microphone amplifier. So the 5 volts will not be there. But at the moment, I'm having to connect it separately. So that's why the microphone's still working. Right, okay, what I'm going to do is I'm going to flick the button on the screen now to engage the tuning tone. You have to take my word for it. And now, you've already seen now, it's dropped out, and that's because I've switched out the microphone now by doing that. Now, if I engage the PTT, there you are. And the microphone's not engaged at all. And that is giving us that tuning tone, which is certainly not a sine wave, but is more sinusoidal than it is square. and so we're going to use that for tuning purposes. And if I kill that off then. So yeah, so fantastic. It does what I wanted it to do.
So I've got a microphone amplifier with a compressor that actually compresses. Brilliant. Now, the next video, what we're going to do is we're going to put together all these different modules that I've been building and showing you about, the whole lot of them, which means the microphone amplifier, all the IF section that I've been building, the post mixer amplifier, which I haven't told you about because it's just another one of those identical tier amps that I built in the last video, and the bandpass filters. Remember them right at the beginning of this this video series? Put the whole lot together and we're going to do some transmit testing. Very exciting. So that's coming up next time, but until then, thank you ever so much for watching. If you haven't subscribed, please do. If you've got any questions or comments, then by all means leave them below as well. But look after yourselves and I'll see you on the next video. Thank you. Bye-bye.